You probably started your day interacting with plastic. Maybe it was the wrapper on your breakfast bar, the handle of your toothbrush, or, I don't know, the casing of your phone.
Oh, definitely. Plastics are absolutely everywhere.
They are incredibly versatile, right?
Hmm.
They enable so much of modern life. Durable, lightweight, moldable, cheap.
Exactly. But we're also increasingly aware, really acutely aware now, of the massive environmental footprint they leave behind.
Yeah, and not just the waste problem, but how they're made in the first place.
That's the critical piece, isn't it? Often overlooks the production stage. The vast majority of plastics today, made from fossil fuels, basically locking up ancient carbon and then releasing new carbon during manufacturing.
With demand just going up and up.
Right. Global demand for plastic is projected to keep rising significantly. So finding truly sustainable ways to produce these essential materials isn't just important. It's, well, arguably one of the most pressing challenges for our planet's future.
Absolutely. And that's precisely what we're diving into today. We're exploring a really cutting-edge, kind of fascinating idea. Making plastic in a fundamentally new way.
How so?
Potentially using captured CO2, yes, carbon dioxide that's already out there, or in industrial emissions, and coupling that with renewable electricity.
It sounds almost like science fiction, doesn't it? Taking greenhouse gases and turning them into something useful.
It does, but it's based on real technology that's under active development and scrutiny right now.
Indeed. And to ground our exploration, we're pulling insights directly from a specific, pretty detailed analysis. Our deep dive today is guided by the findings presented in the study titled Climate and Biodiversity Impacts of Low-Density Polyethylene Production from CO2 and Electricity in Comparison to Bio-Based Polyethylene.
Okay, so our mission today is to really unpack this study's findings. We want to understand exactly what it discovered about the environmental footprint of this new CO2-based approach.
How it stacks up, basically.
Yeah, how does it stack up against traditional fossil-based plastic, our current standard, and also against some existing bio-based options? We're going to look specifically at two major environmental factors this study focused on. Climate impacts, so the carbon footprint,
Mm-hmm.
and biodiversity impacts, particularly those related to land use. And I can tell you right now, some of the things this study found are, well, pretty surprising. Might challenge some common assumptions about what sustainable plastic really means.
It's a deep dive into the data, really, to try and see the full environmental picture, moving beyond just single metrics or, gut feelings.
All right, let's start at the beginning then. How does this actually work? We're talking about making polyethylene. That's a super common plastic, right? Bags, films, packaging.
Flexible pipes, lots of things. Low-density polyethylene, or LDPE in this case.
Right, LDPE, from CO2 and electricity. Can you walk us through the concept? Plastic from captured emissions or thin air?
Yeah, sort of thin air. The process this study investigates is a type of power-to-X pathway, often just called PTX.
Power to.
The core idea is using electricity to power chemical reactions that convert simple molecules, specifically captured CO2 and water, into the more complex chemicals you need to build plastics.
Okay, captured CO2 and water. How do they get turned into the building blocks?
It's a multi-step chemical chain. First, you need your CO2 source. This study looked at capturing CO2 from industrial flue gases, think power plants, cement factories,
Okay,
or even directly from the atmosphere using direct air capture, DAC. That's your carbon feedstock.
got it. Carbon atoms from CO2. Where do the hydrogen atoms come from?
That's where the water and electricity come in. Hydrogen is produced from water through electrolysis.
Right, splitting water.
Exactly. Using electrical current to split H2O into hydrogen and oxygen. This step is crucial and often very energy intensive.
Okay, so you've got captured CO2 and you've got hydrogen made using electricity. What's next on the path to plastic?
You react the hydrogen and the captured CO2 together. This initial reaction makes methanol.
Methanol. Okay, I've heard of that.
Yeah, it's a versatile chemical intermediate. From methanol, you then convert it into lighter molecules called olefins, specifically ethylene in this case, through a process called methanol to olefins, or MTO.
Ethylene. Okay, now we're getting somewhere. That's the fundamental building block for polyethylene, right?
Precisely. Once you have the ethylene, the final step is polymerization. You link lots of ethylene molecules together to form those long chains that make up polyethylene in this study, LDPE.
So the chain is capture CO2,
Mhm.
add water and electricity, make hydrogen, react H2 and CO2 to get methanol,
Mhm.
convert that to ethylene, then polymerize to LDPE.
Phew. That's the sequence. CO2 capture, electrolysis, methanol synthesis, MTO, polymerization.
Wow. So instead of cracking fossil fuels like oil or gas for ethylene, You're essentially building it up from captured carbon and water using electricity. It's a totally different starting point.
Fundamentally changes the raw materials and the energy source. Yeah, that's the from thin air sort of part, taking existing or waste carbon and building with it.
It reimagines the whole feedstock basis, aiming to decouple plastic from fossil resources.
That's the goal.
Okay, now let's get to maybe the headline-grabbing part, or at least the most surprising finding from this study: climate impacts. Carbon footprint. The study suggests the CO2-based plastic pathway can actually have a negative carbon footprint. That sounds completely counterintuitive for making anything. How is that even possible?
This is indeed one of the most significant takeaways, and yeah, maybe confusing at first glance. A negative carbon footprint means the overall process cradle to gate in this analysis results in a net removal of CO2 equivalent from the atmosphere, not an addition.
Removal.
Yes, and the study shows this is achievable, but under two critical conditions examined in their modeling.
Okay, what are those two conditions? Got to be important.
Absolutely critical. First, the electricity used throughout the entire process chain has to come from renewables. We're talking 100% renewable electricity, wind, solar, maybe bioenergy-derived electricity.
Yeah, clean energy and non-negotiable.
Totally essential because, like we just said, electrolysis is so energy hungry. Using fossil fuel electricity would just shift the emissions problem upstream. You wouldn't gain anything.
Makes sense. What's the second condition?
The second condition is about the carbon accounting, how you count the carbon. The study applies standard life cycle assessment methods, referencing principles like ISO 14067 for product carbon footprints.
Okay.
Under these standards, if you capture CO2 from the atmosphere, like with D, or from a biogenic source, maybe a pulp mill or a bioenergy plant, and you lock that carbon into a stable product like plastic,
You get credit for it.
you can credit the system for that removed or avoided CO2. So the second condition is accounting for the carbon that is captured and effectively stored within the plastic product itself for its lifetime.
So the negative number comes from using zero-emission energy plus counting the carbon that's now trapped inside the plastic instead of floating around.
That's the logic applied in this study, yes. Use renewable energy, you minimize or kill the process emissions. Capture CO2 and store it in the plastic, you effectively remove CO2 from the air or prevent its release elsewhere. If the amount captured and stored is more than the unavoidable process emissions, even with renewables,
The net result is negative.
wow.
That's the potential.
And I guess if you don't use renewable energy, this whole negative idea goes out the window.
Absolutely. Forget about it. The study explicitly contrasted the renewable scenarios with ones using, say, a typical grid mix electricity or natural gas for energy. In those cases, the carbon footprint was positive, often significantly positive. And the composition of the local grid mix, how dirty or clean it is, had a massive impact, as you'd expect. A dirtier grid meant a much higher footprint for this PTPE process.
Right, you're not solving anything if your clean process runs on coal power. So you mentioned the energy-intensive steps. Which part of this PTPE pathway is the main culprit for the carbon footprint, even in the best-case renewable scenarios? The study clearly points to electrolysis, splitting water into hydrogen and oxygen using electricity. That's the big one.
How big?
Depending on the specific scenario and the electricity source modeled, this single step could account for, get this, 52% to 83% of the total carbon footprint.
Whoa. 52 to 83% just from splitting water.
Yeah. It really highlights just how critical the efficiency of those electrolyzers is, and of course, the source of the electricity powering them.
That's the bottleneck then.
Absolutely. The study's sensitivity analysis backed this up. It showed that making electrolyzers more energy efficient is a key lever for pushing that carbon footprint down even further in the future. Big potential for improvement there.
Okay, so renewable electricity plus accounting for stored carbon equals a potential negative footprint. Yeah. How does this actually compare to the plastics we use now, like standard fossil-based LDPE or those bio-based alternatives you see?
Good question. This study directly compared the PTPE results to benchmark figures from existing literature. For fossil-based LDPE, as you'd guess, it's got a positive carbon footprint. The literature cited by this study puts it around 2.9 kilograms of CO2 equivalent per kilogram of LDPE.
Okay, 2.9 positive.
Right. The renewable PTPE scenarios in this study showed a substantial emission reduction compared to that fossil benchmark, so definitely an improvement over traditional plastic.
Better than fossils, a good start. What about versus bio-based, like that sugarcane-based polyethylene that some brands use?
Yeah, they compared it to a sugarcane-based HDPE pathway, high-density PE in that case, but similar principles. That pathway is known, in the literature they cited, for having a negative carbon footprint, around negative 3.09 kilograms CO2 equivalent per kg.
Even more negative than the potential PTPE.
Well, interestingly, this study's renewable PTPE pathway, when you count the stored carbon and use 100% renewable energy, seemed to have a slightly higher carbon footprint, so less negative than that specific sugarcane benchmark they used, maybe around 6.5% higher, according to their numbers.
Huh. So wait a minute. On just the pure carbon number, counting stored carbon, this fancy CO2-based plastic isn't necessarily the absolute best compared to all bio-based options. That's surprising.
Not necessarily better than that specific high-performing sugarcane example based on the literature figures they referenced. It's important context. The study also mentioned other bio-based PE options, like one from corn stover, which actually had a higher carbon footprint reported in the literature compared to this renewable PTPE.
Ah,
It really hammers home a crucial point. Bio-based doesn't automatically mean lowest carbon footprint. It depends hugely on the specific crop, the farming methods, and especially the energy sources and processes used to convert that biomass into plastic. Whether it's bio-based, fossil-based, or CO2-based, the process and energy are critical. There's huge variation.
that's a really important nuance, and it brings up something else we touched on, counting the stored carbon. That negative footprint relies on the carbon staying put in the plastic, right?
Exactly.
But if that plastic is, I don't know, single-use packaging that gets burned after a few weeks.
Then that captured carbon goes right back into the atmosphere. The storage benefit is lost.
So the end of life really matters here.
Massively. You're hitting on a key point the study discussed. Even though they deliberately excluded the end-of-life phase from their core carbon footprint comparison results, just to focus cleanly on production. But yes, the climate benefit from storing captured carbon is only realized if it stays sequestered.
So longer life products are better for this, like pipes or building materials.
Exactly. Or effective recycling that keeps the carbon locked up longer, delays incineration, or maybe secure landfilling. Short life incineration undermines that storage aspect.
Okay, so follow-up question. If you don't count the stored carbon, maybe because you know the plastic's going to be incinerated quickly, how does renewable PTPE look then, just on its production emissions?
Still pretty good, actually. The study indicated that if you just look at the production carbon footprint, the emissions from manufacturing, before any storage credit, the renewable PTPE pathway is still much, much lower than fossil PE. And importantly, even without that storage credit, its production footprint is similar to, or potentially even lower than, some bio-based PE options, especially those that might use non-renewable energy during their production.
Okay, that clarifies things. Even just looking at the factory gate emissions, using renewable energy to make plastic this way has big advantages over fossil fuels. The potential for a truly net negative footprint depends heavily on what happens after the plastic leaves the factory.
Precisely. End-of-life management is absolutely tied to the overall climate impact picture here.
Okay, let's switch gears slightly. This study also looked beyond climate change at another really critical factor: biodiversity impacts. How do they assess that, and what did they find comparing this PTPE pathway to bio-based options?
Right. Biodiversity loss is a huge issue, and land use change is a major driver. So this study focused on evaluating the land use-related biodiversity impacts.
How do you even measure that?
They used a method that considers three main things for each material pathway. First, just the sheer area of land required. Second, the Hemmerby level of that land.
Hemmerby, what's that?
It's basically a measure of how intensely humans use or influence the land, how far it is from a natural, undisturbed state. Low Hemmerby means closer to natural. High Hemmerby means very disturbed, like intensive farmland or an industrial site.
Okay, area and intensity of use. What's the third?
The intrinsic biodiversity value of the specific ecoregion where the land use happens. Using land in a biodiversity hotspot is different from using land in a less diverse area.
Got it. So it's not just how much land, but what kind of land and where it is. Makes sense. Converting a rainforest versus a parking lot.
Exactly. And the study found a particularly significant land use impact for one of the key comparisons: sugarcane-based PE.
The bio-based one again? Why?
Sugarcane cultivation, naturally, requires a substantial land area to grow the feedstock. Their assessment estimated around 3.5 square meters of land per kilogram of PE produced.
Wow. 3.5 square meters for 1 kilo of plastic. That adds up quickly.
It does. And crucially, this land use often happens in ecoregions that have high natural biodiversity values. Plus, intensive agriculture like sugarcane farming results in a high Hemmerby level. The land is heavily modified. That combination makes it a major contributor to biodiversity loss, specifically from this land use perspective.
That makes intuitive sense, I guess. Growing crops take space, often valuable space.
Right. Now, compare that to the land use impacts of the PTPE pathway described in the study. Most of the core process steps, electrolysis, synthesis, polymerization, they happen in industrial facilities.
Factories.
Yeah. They need land, of course, but the land required per kilogram of plastic produced is relatively low compared to farming sugarcane.
So the factories themselves aren't the big land users here.
Not in the same way, no. For the PTPE pathway, the main variable for land use and its associated biodiversity impact shifts significantly. It becomes about the land needed for energy production.
Right.
Mm.
Especially if you're using renewables like solar or wind, which need space for panels or turbines.
Exactly. It's not feedstock farming, it's energy farming, if you will.
So how did that comparison turn out? Land for sugarcane versus land for solar panels or wind turbines to make the same amount of plastic?
This was another really striking finding in the study. If the PTTC process they modeled is fully electric, meaning heat also comes from electricity and uses renewable electricity from sources like wind or solar,
Yeah.
its biodiversity impacts from a land use perspective are substantially smaller than the sugarcane-based PE benchmark.
How much smaller?
The study estimated a potential reduction of over 96% in land use-related biodiversity impacts compared to that sugarcane pathway.
Over 96% reduction.
Yeah.
That's massive. So even though solar and wind farms take up land, their impact per kilo of plastic produced seems way, way lower than growing sugarcane for it.
That's what this specific land use-related biodiversity impact assessment strongly suggests, yes. While renewables do have land footprints, the amount of land needed per unit of energy, and often the possibility of using land that's already degraded or less biodiverse compared to prime agricultural land. Well, it results in a much lower calculated impact per kilogram of plastic made via the fully electric PTPE process in the study compared to the sugarcane benchmark.
Were there any scenarios where the PDPE pathway didn't look so good on biodiversity?
Yes, absolutely. There was a significant caveat highlighted. If the PTPE process relies on forest biomass for heat or other energy needs, which was one scenario they looked at that changes the picture dramatically.
Also,
Using forest biomass requires significant land use for forestry, for harvesting. Depending on how that biomass is sourced and managed, is it sustainable forestry or is it contributing to deforestation? This can lead to biodiversity impacts that could potentially exceed even those of sugarcane PE, particularly if it happens in sensitive biodiverse forest areas.
wow. So the energy source is critical for biodiversity too, not just the carbon footprint. Electric renewables look good on land use. Biomass is a potential red flag depending on the source.
Exactly. Very source dependent.
Did they say anything interesting about solar farms specifically, beyond just the area they take up?
Yeah, there was a neat point about the nuances of solar PV land use.
Huh.
While the ground directly under the panels might be heavily modified, have a high Hemmerby level,
Right.
the areas between the panels or around the arrays can potentially maintain higher biodiversity, a lower Hemmerby level. They also cited some research suggesting that solar parks, if sited thoughtfully, maybe on degraded land or former farmland, could potentially even enhance local biodiversity over time.
Huh. Interesting. Maybe create different habitats.
Possibly. And some suggestion they might create cool islands in arid places, which could have knock-on benefits.
That's a valuable detail. It's not just a black box footprint. Management and location matter.
Okay, so this study paints a really complex, but, potentially very promising picture for making plastic from CO2 and renewable electricity. What are some of the bigger picture implications, maybe limitations or remaining questions this kind of analysis brings up?
Well, one crucial implication, as we discussed quite a bit, relates to the plastic's end of life. The study focused on production impacts, cradle to gate, but they emphasized how important the end is. That stored carbon only helps the climate if it stays locked away.
Right. Packaging that gets burned quickly doesn't really deliver that benefit.
Exactly. So the system design, how we use the plastic, how we manage the waste, is paramount if we want to maximize any climate benefit from CO2-based plastics.
Makes sense. Making it is just step one. The whole life cycle matters. What about the source of the CO2 itself? Does it matter where it comes from? Absolutely critical for long-term sustainability. Yes. Capturing CO2 from, say, a coal plant's flue gas is technically possible now, and maybe it's a transitional source. But truly sustainable production needs CO2 from non-fossil sources.
What?
The study highlighted options like capturing CO2 from bioenergy plants, especially if they also capture the carbon, so BECCU, or from waste incineration, maybe pulp and paper mills that process biomass. And looking ahead, direct air capture, DIC, literally pulling CO2 from the ambient air, becomes really important for scaling up sustainably.
So you don't want your sustainable plastic to depend on keeping fossil fuel plants running.
Precisely. Relying on fossil industry emissions isn't a viable long-term feedstock in a low-carbon future.
Okay. What about scale? Can this technology realistically make a dent? Can it replace a significant chunk of the world's plastic?
That's a key question, and the study touched upon a potential scalability advantage for this PTPE pathway, especially compared to some bio-based plastics.
Oh, so?
It's not tied to limited agricultural land. It doesn't compete directly with food production for that land, which is a huge challenge for many bio-based materials, right?
Right.
Especially as the global population and food demand keep growing.
That's a major bottleneck for biofuels and bioplastics, yeah.
This analysis suggests PTPE is a potentially globally scalable pathway. It relies on abundant resources, CO2 from the air or various industrial streams, water powered by renewable electricity, which is also scaling up. Given how much plastic demand is projected to increase, maybe triple by 2060, according to some estimates, cited scalability is absolutely critical for any real sustainable alternative.
Not competing with food, globally scalable. That does sound like a potential major advantage for meeting future demand more sustainably. Did the authors mention any limitations or specific assumptions in this particular study that we should keep in mind?
Yes, they were quite transparent about the scope and limitations. We already talked about excluding end of life from the main comparison. They also noted their model of the PTPE process might not represent a fully optimized industrial plant yet. For instance, maybe it didn't fully utilize all the potential waste heat from different steps. A real-world plant might be able to capture and reuse more heat, potentially lowering energy demand and the footprint, especially if some heat wasn't coming from renewables.
Okay, so real-world performance could potentially be even better with optimization.
Could be. There were also the usual limitations around data age for some process steps, and the fact that the biodiversity method they used, while advanced for land use, didn't cover everything like water use impacts, pollution, toxicity. They acknowledged land use is currently the most developed method for this kind of comparison, though.
So it provides really valuable insights, but it's a snapshot based on current knowledge and data. There's still room for improvement in the tech and maybe refinement in the analysis methods down the line.
Exactly. It lays a strong analytical foundation and definitely points the way for future R&D and assessment.
Okay, so let's bring this all back home for you, the listener. You've now taken this deep dive with us into the findings of this important study. You've seen that producing low-density polyethylene from captured CO2 and renewable electricity isn't just some sci-fi concept anymore.
No, it's a real pathway being rigorously analyzed with potentially significant environmental implications.
You've seen the potential for actually achieving a negative carbon footprint during production.
But, and it's a big but, that hinges completely on using 100% renewable energy and depends crucially on what happens to the carbon stored in the plastic over its whole life.
Right. And we've also seen this really compelling possibility of dramatically lower land use-related biodiversity impacts compared to a common bio-based option like sugarcane PE.
Especially if the process goes fully electric, powered by renewables like wind or solar, avoiding that tricky biomass land use issue.
But we've also heard the nuances, haven't we? The complexities. It's definitely not a simple case of one technology being just good and another bad.
Not at all. The specific energy source powering any plastic production, whether it's fossil, bio, or CO2-based, is absolutely critical for both climate and biodiversity impacts.
And factors like what happens at the plastic's end of life, and ensuring the CO2 source itself is genuinely sustainable. They matter hugely for the overall environmental picture.
It really demands a holistic view, a systems thinking approach. You can't just look at one piece in isolation.
Which leaves us with some really interesting, maybe even provocative thoughts to chew on. For instance, based on this study, how do we weigh these trade-offs?
Yeah, like is a slightly higher carbon footprint in production for renewable PTPE compared to that specific super optimized sugarcane PE example? Maybe an acceptable trade-off if it means drastically reducing the pressure on land and avoiding potentially huge biodiversity impacts, especially with plastic demand soaring and land getting scarcer.
That's a tough calculation. What else?
Or Thinking bigger picture, how can we actually design the entire plastic system from making it with captured carbon to designing products for durability and easy recycling to managing waste streams? How can we design that whole system to maximize the temporary carbon storage benefit that these CO2-based plastics might offer?
How do we make sure that captured carbon stays locked up for as long as humanly possible?
Yeah, exactly. These are complex questions, right? They go way beyond just the factory gate. They force us to think about the whole life cycle, the whole system.
And it all stems from exploring and analyzing new possibilities, like the ones laid out in the study that guided our conversation today. Climate and biodiversity impacts of low-density polyethylene production from CO2 and electricity in comparison to bio-based polyethylene.
A powerful reminder, I think, that the choices we make about the materials that literally build our world, and especially how we produce them, have these really complex, cascading effects through the environment.
The effects we really need to understand fully as we look for more sustainable paths forward.
A truly fascinating and critical area of research for the future, no doubt about it.